when do I look at a sample? When do I look at a population? And usually it'll be obvious in the problem because they'll say from a sample of 500, or the sample of 500 is drawn from the population, or something, whatever it will say. So basically you're looking for your mean to be the same, but your standard deviation to get smaller. It puts your curve closer to the mean. It took a Y curve, and all it did was centered about the mean and popped it up like that. Your standard deviation got closer to the mean. There was less variance. This is all we get out of this. So here's a good example of how are we doing this. They just want us to find your mean and your standard error of the mean. That's your standard deviation for your sample. Cell phone bills for residents of a city. Here's your population. Residents of an entire city. Here's your population. Have a mean of 47 and a standard deviation of $9. Random samples of 100 cell phone bills are drawn from this population. They don't tell us how many samples, they just tell us what the sample size is. So from a city, they're generating 100 people at a time to find that mean. All of those sample means, they will take one mean from, one average of all those averages. And that mean will be exactly the same as your population mean. So they want to know the mean and the standard error of the mean of the sampling distribution. The sampling distribution are all your sample means. Remember, he had a hard time keep saying this himself. There was like a tongue twister thing. We know this is true, so our sample mean is exactly the same. This is all you have to do. There's no difference so far. Here's your difference. The standard error of the mean says take the population standard deviation and divide it by the square root of n. So we say n is 100. One other little piece of information to pull out. So we're going to take the standard deviation and we're going to divide it by the square root of 100. And what's the square root of 100? 10. So this is 9/10 or 0.9. Now, look at the difference, guys. Here's my population. This was my population. Here's my sample. My sample says my mean is still the same. My standard deviation for my sample is now 0.9. Look at how that increased. God bless you. Now, here's the difference also. Here's your original graph. 47, and we add 9. So 56, 65, 74. And we subtract 9. 58, 49, 40. This is your population, right? Your mean, I added 9, standard deviation. This was your population graph.
You added 9 to the
This one right here. I'm doing your population. You know how you add 9, then you subtract 9? This is my standard deviation of 0, 1, 2, 3.
So you subtracted 9 for 47.
And then I look, I guess, and I can't subtract.
Oh.
38, 29. Is that what you were worried about, my subtraction?
Nah, because I was really confused.
I was confused too. I can't talk and subtract at the same time. Okay, feel free to stop me whenever I'm wrong. Okay, now, do you see your distribution here? Okay, now, watch what happens when I change this guy to a standard deviation of 0.9. 0.9 would give me 47.9. There's my 1. I would add another 0.9. That's 47.9. 48.8. See how close it is in here? Here's my 3. Look where my graph is going like this. Look how close to the mean I am. It took your standard deviation and shrunk it down. about the mean. The mean stayed the same. So our curve now is this small. But here's what we're going to do. When we graph these and you give me a sketch, I don't want both of them together because it's way too confusing. And when we go to work with this little green one, it's really impossible for you to put 1, 2, 3 standard deviations in that little space, isn't it? So when we do this, we're still going to just spread this out. We're going to put your mean here, and we're going to add 0.9, 47.9. We're going to add 0.9 again, 58.8, and we're going to add 0.9 again. We're going to make it look like this, but in reality, it's that narrow. Do you understand what I'm saying? Because if we had to work with the both of those superimposed on each other like that, there's no way you're going to be able to figure out where the pieces are. So once we understand that concept, we're still going to spread it out so that now, where is 47.6? Oh, there's 47.6. Less than 47.6? More than 47.6? Between two numbers, we'll be able to see it better. Okay? Now, some of you are looking at me like I have 5 heads. Okay, now, I unfortunately erased this, but let's go back to this part. Up here, we found your standard error. We found this to be this, and we found your standard error of the mean to be 0.9, right? Now, that was a sample size of 100. We're going to do the same thing, but we only are going to do a sample size of 64. Which one is it going to change, the mean or the standard deviation? Standard deviation. The mean is going to stay exactly the same. But the standard deviation is going to say take 9 divided by the square root of this new n, which is dividing by 8 instead of 10, right? So now I'm 1.125, thank you. My standard deviation is a little bit bigger. So what we notice is, as the sample size gets larger, I'm dividing by a larger number, so it should give me a smaller standard deviation, right?
So we use the 1.125.
For this guy. And so then when we make our curve for this, we're going to put the 47 here, and then add 1.125, 48.125. And then we're going to add another one. We're going to map ours out like this, because if we did it together, they'd be squished into that little space like this. You wouldn't be able to say, where is it less than, where is it greater than, where is it in between. You wouldn't fit it on there. So we're going to spread it out again anyway. All right? But you can see that as your standard deviation is the guy that controls the spread of this. And that is controlled by your sample size. So I don't know if you caught yesterday on his, or the day before, or Friday. Friday, you saw the video. Tuesday. Okay, Tuesday. Tuesday, you saw the video. I don't know if you caught, like, when he did it like 1,000 times and then he did it 10,000 times. Yeah, it got closer and closer. The kurtosis is how it's how tight it is, how positive it is above that. And we don't really use it kurtosis because we push in anyway. We push it in anyway. But that's what he was basically getting at. Your kurtosis is hard to measure on that because he still had a little bit of a negative kurtosis, even though we see it push up. But he still got a negative kurtosis. So that's why I kind of didn't dwell on that one, because it would look like a positive kurtosis because it came above the curve, which I would think. So when the kurtosis still showed a little bit negative, you saw the negative decreasing till it was very, very close to 0. Because now it's almost a perfect. You know, as your standard deviation gets larger and larger, you get a more perfect situation. This is what he was trying to get at. Okay, so now, let's see how this affects us. Assume the training heart rates of all 20-year-old athletes are normally distributed. Ah, look what they told us. They are normally distributed. So I know my population looks like this. So now does it matter what size sample I use? No, because my population is normally distributed with a population mean of 135 and a standard deviation of 18 beats per minute. And they showed you a figure there. Random sample size of 4. This is your N. pull this out as well, are drawn from this population, and the mean of the sample is determined. You need to find the mean and the standard deviation of your sampling distribution. Now, because our population is normally distributed, we can use your central limit theorem. Here's the difference. If they did not tell us this, if they did not say normally distributed, and they told us our sample size was 4, we had to say we cannot use the central limit theorem because I don't know if my population is normally distributed. A small sample size, if you remember when he did it, remember when he did the 5? It was starting to get a little normal looking, but not really. So 4 would be way too small. But because they told us it is normally distributed, we're okay with 4. So the mean is the same as the mean. So here's our mean. And our standard deviation, our standard error of the mean, says take the standard deviation and divide by the square root of n. So you're going to take their standard deviation and divide it by how many, square root of how many are in your sample. So this standard deviation will come out to say 9. So look at, already it got smaller, didn't it? And again, if we did your population, just briefly, I did a 135. If I add 18, 153. If I add 18, 171. I'll just do that side. My mean is going to stay the same, but now I'm going to add 9. So my 1 now would be here at 143. I add another 9, 152. There's my standard deviation of 2. See it? So technically, I'm going like this. I'm pushing it in. Pushing it in. My standard deviation shrunk. So when we sketch this, in reality, this is what it looks like. But because we're never going to be able to like fit all our stuff in here, and it's not really going to look as nice, we're just going to lay it out like this. Standard deviation, we'll just count from our samples only. And we'll add the 9. 143, 152, 161. We'll just lay it out like this because obviously you're going to get more to your problem. It's going to say what's the percentage of having less than 150 in the sample, greater than such and such. You need to be able to look at the percentages as well. Are we okay with this? This was this whole thing that we went through the videos and we went through everything just to do that little thing.
What happened with charts? What do we do on charts?
The charts, what the charts did, once we get one of these, I think you're going to see a big difference. Now, here's your standard z-score. This is your standard z-score formula for your population. You choose one x value out of a population of, all the users of the internet in the United States. You choose one person. That's your x value. And you find the z-score and you see if it's less than, greater than, whatever it is you're looking at. This is from your population. From your samples, you're going to do the same thing. Only difference is you're going to do your x minus the mean over the standard deviation divided by the square root of n. This is the only difference that you're going to see, is your standard deviation changed. The only difference. We're going to graph the curve that fits our sampling distribution, otherwise we're not going to fit anything on it. And we're going to do one right now. As a matter of fact, if you want, we'll compare the population to the sample if you want to do it and see what the difference is. Okay? All right, so let's take a look at this. This is the whole business of this. Yeah. Well, the problem with this theorem is it's so hard to explain, but as soon as you use it, you say, is that all we had to do? But I don't want you to say, oh, just plug it into this formula, that's all we have to do when we see this. I want you to understand it. It is one of the major concepts in statistics. Okay. You randomly select 50 drivers. This is your sample size. Normally, wouldn't we say we randomly select a driver? A driver. I'm going to do population I'm going to do it a little different than them. Versus sample. Okay. Now, 50 drivers. Does it matter what our population looked like? What shape it was?
No.
What's our cutoff for N?
30.
30. So N is greater than or equal to 30. So we're okay with that. We're in here. We're going to assume our population was normally distributed, or I can't do this part. Okay, what is the probability that the mean time they spend driving each day is between these 2 minutes? The probability that they're between 24.7 and 25.5 minutes per day. Okay? Now, we're going to assume that your standard deviation is 1.5. Only thing I'm missing is the x value, which I'm sure I probably forgot to write down. Probably is off the chart, right? So in the 15 to 19 group, what is their mean? Look at your chart on page 266. What is their mean from the chart? 25 minutes. Their mean from the chart is 25 minutes. Now, if I randomly selected a person, watch the difference. Here's my curve. 25. I'm going to add 1.5. 26.5. Add 1.5. 28. 29.5. This is not what it's asking, but I want to show you population versus sample. I subtract 1.5. Okay, this is what my curve looks like. Agree? So my 24.7 to 25.5 is coming in between here somewhere. Agree? All right. Let's find your z-score for those things. Come on, stand up. All right. So we did, when x is 24.7, we did the z-score is x minus the mean over the standard deviation. 24.7 minus 25 over 1.5. I need someone to do this for me because this one's not in the book. I'm doing this different than the book is. So what did we get? Negative 0.2. Thank you. Negative 0.2. And doesn't that make sense? It's real close here. Now we're going to do this when x is 25.5. So if someone doesn't mind doing this one, 5 divided by 1.5 divided by 1.5. So 0.33. Okay? And that certainly makes sense. Now, how do we find the area in between? We look up your z-scores. Hang in there, guys. We find the area for this one. We find the area for this one, and then we subtract your areas. So if somebody's using a handy chart, let's find your areas. I want you to see the difference because this is really why we use this. So negative 0.2, 0.6292.
6.293.
Okay, and for negative 0.2, 0.4207. We could have easily did this in a step in your calc, but I didn't want to because I wanted you to see the standard deviation. 0.6293 minus 0.4207. What do we get? 2086. About 21%, right? About the area is about 21%. The probability is about 21%. Now, no. That's from your population. Now, your question is asking, didn't we used to do this before? This is the way we exactly did this before.
Oh, yeah.
Okay, now, watch. The only difference we're going to do now is find a new standard deviation. We're going to take your standard deviation divided by the square root of n. We're going to take your 1.5 divided by the square root of 50. And if we could do that, So it's approximately 212. Let's just say 21, okay? Is that good? Approximately 0.21. Look at your standard deviation. It was 1.5. It shrunk down to 0.21. Watch what it does on your curve. I'm going to spread the curve out. This is what I was talking about. If I put it in here, look how little it's going to be. It's going to be like this, isn't it? It's going to be a little tiny thing in there. We're never going to be able to see where our numbers are. So we're going to start with your mean. And we're going to do our own curve for this.
So the area gets smaller too.
The area is going to be a lot smaller. It's not going to appear so on our graph because your graph is really in here. But because, how are we going to work with that? We can't. So we're going to do our same process. 25.21, I add another 0.21, 25.42, I add another 21, 25.63. I subtract 21, 24.79, I subtract 21, 24.58, thank you, and that's probably good enough. Now, I need to know between 24.7 and 25.5. I need to know this area. Okay? Remember, it's going to be a little tiny area. I don't want to deceive you by you thinking it's going to be very large.
Same thing, you just fill in a different standard deviation.
You're giving it is a lot
Yeah.
spread out.
Yes, it's technically
Technically the exact same thing. You just changed your standard deviation because look, z-score. So now, when x is 24.7, I'm covering more area. Isn't all that area 100% is squeezed into this little piece? All I did was spread it out so you could kind of see it better. If we did your area and your area came out to be like 80%, would you believe it's in this little piece? Because this whole 100% is in that little green thing. So we spread it out. So watch. 24.7 minus the mean over the standard deviation divided by the square root of n, which is what we found. So we find your z-score to be what? They have the z-score. I can pull up their z-score. To be negative 1.41. Doesn't that look so here? Was I going to be able to see it over here? 100% of your green area is flowing in here. How hard is that to fit that into that little tiny space? Can I now see that my area is going to be large? My area is going to be larger, isn't it? The space between this is narrow, but 100% of my curve got squished into there. Now, I do the z-score for this guy. Same way. But my standard deviation says take the square root of 50. And my z-score for this guy is 2.36. Aren't I between the 2 and the 3? That would be so hard to tell in this little piece right here. I have a lot of area sitting in that little tiny space. But if I spread it out, don't I see it better? But I want you to realize it came from here. We just spread it out so we could work with it. Yeah, and this is where you're going to see the biggest difference. Look up your area for this, look up your area for this, and I think they did, so I think we can just subtract their areas. So we're going to get 0.9909 minus 0.0793, 9116. Were you able to realize that 91% came within this little space? That little space has 100% of your area. This is 100% of your curve in there. But you really, really can't tell how much of your area is there until we look at it spread out. Do you see the difference? Is it better for me to run a sample of 50 or to pick one person at random? Sample. And didn't we say that previously? Wasn't it better for me to use a sample of 50? It would be more realistic for my population rather than picking one person at random. This is one person at random from my population. This is picking from my sample. This looks like it's small, guys, because you put 100% of your area into here. The space between them on this graph is very small. But the space between them when you spread it out is not. It's larger. It's kind of larger when you spread it out. This is 100%. Isn't this also 100%? But If I look at this and I say your area is 0.9, you're going to say, what? It's a little tiny piece of this big thing. But this little tiny piece is 100%. It's 100% squished in here. But we need to see that spread out. Then it makes more sense. It's a better probability to pull from a sample than it is from one person. Yes.